Hello, my name is Jens Struckmeier and I'm founder and CTO of CLOUD&HEAT Technologies. In the next 25 minutes, I'd like to give you an introduction to sustainable data center infrastructure and to solutions we have developed over the last 10 years. So, sustainable and secure data centers with heat recovery. That's the title of today's talk. And I will drive you through a journey. What is the motivation to think about these kind of infrastructures and what will drive the future, how we call it, of compute? First of all, let me quickly introduce myself. I'm a physicist. I founded the company 2010, and we have now more than 90 employees, mainly working in Germany, but we now also have offices in the US, in South America, in Dubai, and we have installations in Japan. So what are the big challenges we are currently facing? One big challenge is growth, and we'll come to that in a little bit later. So if you look at the technology, how it's evolving, we will see that digitalization is basically everywhere. We see that robots are coming more and more into daily life. We see that the car industry is changing towards autonomous driving, and it only becomes possible with a massive amount of data processing and computing technology. We see new mobile standards come up, introduction of the new iPhone and other phones that now support 5G and ultra-fast internet connectivity. And this is needed for virtual reality, for new applications that basically come up. We see also that traditional fields like farming and so on is changing due to the new technology coming up. And of course, that relates to our body and our health. The digitalization in the health industry is rapidly moving on, gaining more and more information, understanding more and more how the biophysics works and also how the body works. That drives a lot of information and data that has been compiled. And there are also technologies that come up that nobody has thought about before, and suddenly they are there. Technologies like blockchain technology. So others will certainly follow, and certainly there will be a new need of computational resources. So the next big challenge is the challenge security. So if we have a lot of data that we are collecting and that we're processing, we have to make sure these data stay protected and that people who generate this data or have value on this data or even have the rights of this data, that they know where are the data and they even can decide if the data stay there or will be deleted. And the other thing is you want to prevent others from stealing your data. So protection of the data is also very important. So encryption plays a major role here. So that's also something that we as our company are addressing if you're talking about the future of compute. And we are active in various areas here, from certification to setting a standard how data center can be certified. We do that in the Auditor project. And there are ISO norms where data security plays a major role. And this is a chance also for even European players to play a major role in the new future of digitalization. Now, the third biggest challenge is sustainability. So we have an increased amount of data on the one hand side. On the other hand side, we want to drive our society to a carbon neutral society, the latest 2050, and get as much done as possible by the year 2030. And there's a conflict here, and I will show you that in a second. If we look at the energy demand of data centers, we will fastly recognize that the energy consumption for data centers in Germany alone is raised from 2010, about 10 billion kilowatt hours per year, to 2030 to almost about 30 billion kilowatt hours per year. So that's already a factor of 3. That's Germany alone, and Germany is not the main country for data centers, as you know. There are other countries where the growth is even much, much higher. To also illustrate the immense energy demand of data centers, you can look at certain examples. For example, an example where you train a robot to solve the Rubik's Cube. So with doing that with trial and error, this requires 2.8 gigawatt hours. And that caused the emission of almost 1,282 tons CO2. So just to get a vision of that, that's 1,500 round trips from Berlin to Chicago. Massive amount of computing data if you approach those problems with massive computing power. So the driving energy demand of data centers is there. On the other hand, this electricity that is used in data centers, that's all converted to heat. And this heat typically is cooled down with air conditioning systems needing additional electricity, right? So, so if you consider the energy consumption of a data center as some heat generation, you have waste heat of about 3.5 million tons CO2 a year you can save if you can use this heat. On the other hand, we see that there are enormous efforts in getting the energy demand of buildings down. So here I have statistics how the energy consumption for buildings kind of goes down over the years between 1996 and 2015. And we see that indeed the private households consume most of the energy for heating. So we see there's a trend here to go towards carbon neutral, but there's a long way to go. On the other hand, we have to look at how you generate then the energy in the future. If you want to heat the buildings, you have to generate that energy. And this graph shows how much percent of the energy type is done renewable already. And we see the blue line is the electricity. So electricity has the renewable percentage of renewable energy in electricity in Germany has raised now up to 42%. But the renewable part of the energy that's used for heat is only 14.5%. So most is indeed fossil fuel that's used to heat the building, and there's only a little bit synthetic fuel and synthetic gas that supplements that. It's even worse if you look at a petrol-driven car. Only 5% of the whole transportation system is fueled by renewable energy. So hopefully that will change with electric cars. But using petroleum to heat the houses, so that should change as well. And of course, one way is to go to heat pumps so you can use electricity. But the other way we will show here is to actually reuse the heat that's generated by other factors, mainly data centers. So we have a map of Frankfurt, and all these little red dots you see here, these are locations where data centers are. As you know, Frankfurt is one of the main data center hubs in Germany. And if you look at these dots, these data centers produce energy that could be used in the surrounding area, basically, to heat up Frankfurt. So this is untapped potential that is there in the cities. And as of today, so far, almost all data centers in Frankfurt, except a very few examples, are not using the heat. They are putting the heat into the air of the city, which brings the major and all the others in the city to the big problem, how to get this city carbon neutral by 2030, which is a goal that Frankfurt had set itself. And then you see newspapers all over the place that say, hey, some of the judgments of how the electricity consumption will evolve is actually wrong. So it's underestimated that the electricity consumption will go up. And part of that increasing of will be digitalization. On the other hand, we see that the European Parliament enhances their goals for climate change and say that till 2030, we want to reduce the climate impact by the factor of the CO2 emission. We want to reduce the CO2 emission by 60%, which is quite a word. So now let's have a look at these data centers. And as I said, it's actually growing. This is a worldwide assumption how the energy consumption of data centers will rise. And you see the data centers as the green block here. You see about also what the consumer devices, how they evolve. They will get better actually, because they want to have a longer battery life. So you put some of the workload also into the cloud. And then you have the production of ICT, so building the devices. So we're talking now more and more about circular economy. So that's an important factor to get the energy amount for producing these devices, getting that down. But as you can see, the prognosis is not it's getting down because you need so much more devices. And then you have the network part. Also, network nowadays is almost computing, right? So you have these massive switches and the wireless stations that kind of connect to the smartphones. So all those need electricity. So we look very much into that. First of all, how can we lower the consumption? That's the first step. And if you have done everything to lower the consumption, the next step is it's converted to heat. So why not using that heat? So that's what we're doing. So let's look at the data centers. So we see the data centers here, and we see that most of the energy goes to the servers. That's of course no surprise. But then you see that's a big chunk that goes to cooling. Well, that can be reduced if you do it smart, right? Also with the servers, you can see where the electricity is going. And we look at this closer, you would see there's also electricity going to fans. Why not removing those fans so that you get this down? Storage has computers in there, so you can do something similar like you do with servers. And then you have uninterrupted power supply and net and other network solutions. And for those, you also want to lower down the energy consumption. So if you do that, that you remove the fans and you put a certain way of liquid cooling, I'll show you how we do that, onto the servers, you can actually reduce the amount of electricity to cool those servers quite a bit. Now, once you have reduced that, as I said, now you can use the remaining energy that's basically used by the server. You can use that as waste heat. And in a lot of places, you can make use, especially in winter, of the heat that comes from these servers, substituting heating demand of the building. So in order to do so, you have to certify, of course, the use of this heat. And we kind of managed to get a certificate that this heat that comes from a data center can be regarded as avoided emissions on other heating systems. So the primary energy factor for heat that comes from data center can be set to 0.0, and this gives the planner of buildings more room to build an efficient building, taking into account that servers are in that building, and he can reuse the energy of those servers. Now that's something one can do, but I want to show you also what currently is done in classical data centers. So you have air cooling. If you do that right, you have a cold aisle and a warm aisle, and you have a circulating air, and you have systems that cool down the air, and with the system, an air conditioning system is typically connected to, right? There are systems where you have so-called side coolers, so put coolers next to the servers, but still you need compression systems, so classical air compression systems to take the heat out of the air and then bring it to the outside. And especially in the summertime, you cannot do that without extra electrical energy. New technologies evolve, like immersion cooling, where you basically dump the whole server in a liquid and in a non-conducting liquid and cool it with this. So it has really some advantages, but there are also complications that it's quite expensive. And there are solutions out there that have been developed over decades now, and we've picked up basically this development, brought it further to direct water cooling, meaning you bring really a cooling loop to the CPU, to the chips, and you pipe the water across this cooling infrastructure, across this heat exchanger, and very closely to the chip, you extract the heat. And that's basically a secret we are doing, extracting the heat directly from the CPU. And then, of course, you need a pump and a pump group, a redundant pump, and a heat exchanger to have a server rack where a circulating water loop is generated to cool down the servers. And this heat now can be extracted, and it can go now to the building. It goes to a buffer tank, for example, and this buffer tank can be hooked up to the heating, floor heating, or to the warm water supply of the building. And if this buffer tank is fully filled because the heat is not needed in the building, this warm water comes back here. And if it's too hot, basically you switch this motor, and then the hot water goes outside to a dry cooler in a closed loop circuit, and the hot water is then cooled down to a level that's acceptable for the servers. Now, cooled down means, in our systems, the server needs a temperature of 55 degrees Celsius or lower, and that's cold enough to cool those servers. I'm talking about 55 degrees, so that's typically hot water, right? But 55 is cold enough with our technology to cool the servers. And the servers heat up this water from 55 to 60 or even higher, And this 60 degrees Celsius is hot enough, right, to be used in a lot of applications and not to be considered as waste heat. If you have just warm air coming from a server, that has literally no value. You want to get rid of that, right? But if you have really hot water coming from the server, it suddenly begins to have a value because you can use it for other things. Now, how do we do that in detail? So this is a server blade that consists of 2 CPUs, and we removed all fans on this server blade. So we put a piping on here with our partner Macware, and these servers are now cooled with the water that comes in here. So you have a quick connector here for electricity and a quick connector for water. So you slide that into a bracket chassis, and it connects automatically to the water and to electricity. So it's pre-filled, and there's a non-spilling valve here so that you don't have to mess around with any kind of water stuff because it's kind of pre-filled, and a quick connector here. So you connected it, and then you get the heat from the memory components here. You get the heat from these components on the back side of the server. These are all the InfiniBand or Ethernet chips that are cooled by this cooling tube. And then the water flows further to the first CPU, the voltage regulator, to the second CPU, to another voltage regulator, across the SSD drives, and basically gets out of the server. So with this kind of setup, we remove all the fans. So that makes this server very low noise, but we also have a very, very slim and compact way of cooling these servers. So why have we chosen to use water as a cooling medium and not air like typical other companies do? Well, the main reason is that air has really its limitations. If it comes to a lot of power, it's very hard to cool that by air. And we know that from the car manufacturer, right? When you have the Porsche in the 90s, they got more and more horsepower in the Porsche. But at some point, they couldn't cool the Porsche good enough. So they switched from air-cooled engines to liquid-cooled engines, and then they could increase the horsepower. So that's something that has been done in the car industry in the past. And by the way, it's done today as well. Like Tesla also is cooling everything with water because it's more efficient than with air. So just a comparison, if you have a data center of 1 megawatt, and you cool that with air, and here are some numbers, but it means you need 84,000 liters per second of air to cool that 1 megawatt data center. If you use water, you only need 24 liters per second. So that's a massive factor of 3,500 between air and water. So it totally makes sense to have a closer look at water, despite that people fear water electricity is a dangerous thing. So that's something you have, or we have addressed. So we are using hot water, 4 times higher energy density. So that is the number of if you have a regular server, you put water cooling in there, you can basically literally crank the space to 1/4 of the space you needed earlier, because you don't need space for the air coming through and so on. And that's even not optimized. You can even have a higher factor of energy density, as we have seen earlier. You can build servers that need no air conditions anymore, right? And you can do a direct heat recovery. Once you have the heat in the water, it's much easier to transport it and bring it into the building where it can be used. And we don't need any fans anymore. So that gives us a 10% extra energy saving by removing those fans. If you have a data center that's liquid cooled, you can place it now next to a building and have it like a local district heating system. You can place it in industrial buildings. You can place it in cities, for example, in a container next to buildings if the space is difficult here inside the skyscraper, or you can have the data center inside the skyscraper and make use of the heat. And we'll see an example in a few minutes. So the last part of my talk, I would show you some use cases, what we have done or what can be done if you really think about the future of computing and the future of data centers. So this is an apartment building that has been built 5 years ago in Dresden, 56 apartments. And in the cellar, we basically placed our service with our heat recovery technology. So you see the piping here. This is all liquid piping. So we need little air here, but the rest is really direct water cooled. And we have 56 apartments that are basically heated with the waste heat of these servers. And we did this together with a local energy provider. So if you want to have a look later on at the hydraulic scheme of this data center, you can have a look here. So we have direct water cooling, and we also have a certain part of hot air that comes also from switches and other components in this data center. So we also integrated a heat pump to make use of the remaining heat losses from electric cabling to some switches, and that part of the heat we can also recover, and with the heat pump put that also in the hot water circuit. We have buffer tanks so that the servers who run at night basically can provide heat that's then needed in the morning when everybody of this apartment complex is doing their shower, is taking their shower. So these kind of things can be used. And the good thing is this apartment complex has not a lot of heating demand because it's insulated very well. It has been built on a very modern energy level, but all year round you have the warm water usage. And to my personal surprise, the warm water usage in the summer is even higher in the winter. I don't know why, but I can only guess that people shower more often in the summer, and maybe they don't shower ice cold. They shower at least with lukewarm water. So it needs apparently a lot of energy also in the summer. So another example is with the energy. They have a glass fiber network where they put these racks into their office locations. It's lower noise, and they could heat, for example, warm water for canteen into their facilities. Now, one more famous use case is the EUROTHEUM. That's the skyscraper in Frankfurt, and has been the skyscraper from the European Central Bank for almost 10 years. Now, the central bank moved out of this skyscraper, and they allowed us basically to take over their infrastructure data center that has been in the skyscraper. The 7th floor and underground floor is a fully replicated data center infrastructure, but it was not very energy efficient, and it was being cooled by a massive air conditioning systems on the roof, which came now with the new hotter summers come to its limits. So we took over the data center. We said we will put our data center inside that building if we are allowed to access to the heat system of the building, so allowing heat recovery of our servers. So the owner agreed. That was the Commerz Real, and we were very happy because now we could install and renovate the data center, put liquid cooling into the data center. Now we can pipe the waste heat of the servers into the heating system of the building, and in the winter we basically supply heat demand to that building. And in the summer, we have 8 floors of hotel up in the skyscraper, so we can provide warm water for the spas and shower purposes for the hotel. And of course, there's a sky bar, the only sky bar in Frankfurt, and the barkeeper wants to wash the glasses and sometimes needs some warm water, so that also can come now from the service. And of course, needless to say that there's a lot of cooling costs you can save just by not needing the air conditioning up in the roof, but also the heating cost can be reduced, and these are quite impressive numbers with 198,000 euros and 65,000 euros for heating per year. So that's quite a bit. And there's also an efficiency value that you can calculate how this looks before the renovation and after. And before the renovation, we had a PUE of 1.92, so that means a lot of energy was wasted. And the new PUE is 1.72, is 1.27. So that means for every kilowatt that goes to the servers, another 270 watt is needed for the infrastructure around it. And most of these 270 watt that's needed for the infrastructure is not going to the cooling, because that's a very small amount now. A lot of it is also going to uninterrupted power supply and these kind of things. In other locations, you would see that the PUE is even lower than that in our data centers. So this is the floor plan of the EUROTHEUM data center, and you see there's a lot of infrastructure belonging to a data center. With the liquid cooling, we have reduced the amount of space we need for the servers. So yeah, there's plenty of space now here. I skipped to the detail how the hydraulic scheme looks like, but I added it to the presentation. So if you're really interested and want to have a closer look at this at a later stage, please feel free to do that. So a few more use cases, and then I can sum up my talk. Another use case is the Deutsche Telekom. They are currently setting up a gaming cloud infrastructure for gaming, which is, of course, for these people like that, a great thing, not to buy the hardware anymore at home, but they can now book it at Deutsche Telekom. On the other hand, it increased the electricity bill of the Deutsche Telekom and the CO2 footprint. So with our technology, we actually help them to reduce the CO2 impact and we hooked up these systems, and Telekom hooked up these systems to their building infrastructure, reusing the heat of the gaming servers. And one simple rack of only has 10 kilowatts of electrical and thermal power. With each rack, we save cooling costs of almost $3,000 a month, a year, and heating cost of 1,800 euros a year. So I added also to this presentation a more detailed look where the energy typically goes. We have a comparison here between the air-cooled system, how that typically works like. I'm not going in all details, but you see that a lot of the electricity comes in, and that's basically converted to air, right? So to warm air. With fans, it's moved out, and then it's going to refrigeration part and generates then waste heat. Even if you have some free cooling going to a dry cooler, it still needs a lot of electricity. So total 86,000 kilowatt hours per year to run such a system. So if you switch to liquid cooling, you immediately see that the electricity is still converted to heat, but the air part is only a small part that goes into air because most of it is captured directly into the heat, into the warm water. And this warm water can be used then in the heating system during the winter time. And in the summertime, the hot water goes out the door through a lower energy heat exchanger and is then as waste heat released into the environment. But this needs much less energy than an air conditioning system. So that sums up to 62,000 kilowatt hours per year. You see a saving of 26,000 kilowatt hours per year just by switching from air cooling to liquid cooling and heat recovery of the data center. So last but not least, the use case is the data center container we have developed. So a modular system that can be placed on places where the energy is generated, like renewable energy, water, and so on, and it can be hooked up to the district heating. And we are proud that we work together with VATTENFAL on these systems. So this is designed to fit VATTENFAL's need to hook that up in the energy infrastructure to have a very, very sustainable way of using the electricity for computing purposes. On the other hand, converting it to heat and use that in a district heating system. And these data centers can have very high power. It's high performance computing. So they have up to 275 kilowatts per container, and they generate a heat of 63 degrees Celsius. And that's a novus because this is very high temperature level that we can guarantee with our control electronics, with our special cooling units and cooling loops we have developed to fit on top of servers. These are servers from classical server manufacturer like Dell, Lenovo, and others, but also systems we have built ourselves. So our vision, and that's a vision that probably comes more and more true, is that despite the big hyperscales that have their hyperscale data centers, there's room for new technology. And that means there's room for distributed data centers. And these data centers should be connected to renewable energy. And if you do that, you can basically reduce the amount of cabling you need to bring the energy somewhere because you just place the data center where you have the energy. And then you can place it on locations where you have cities and pipe the energy that is produced by these servers into the district heating system. And with this, you can heat the buildings and you don't have to need coal or other CO2 emitting energy means to heat those buildings. And the other advantage is if you put the data centers close to the cities to heat them, you also have the data center close to the people who need the services, right? More and more interactive services will come up and the users will use that. And it's pointless to put all the data across the ocean and back. This is also a waste of energy. So processing them locally, it's much easier. And with some of the big data applications, even problematic. It's sometimes even hard to get all these data that the autonomous driving car is collecting, get all these data saved to a pipe through a glass fiber connection because these are massive amounts of data the camera and all these sensors are producing. So with this kind of general impression and wrap up, I want to close my talk. I motivate you to be part of changing the world. Feel free to contact us and enjoy the rest of the day. Thank you very much.